This is Poncat, a MASMA software. We will skip the IDF presentation because IDF is very simple. It's only calculating the rainfall intensity. We will start with OSD, pond and rainwater housing. The contents for this presentation are introduction, MASMA requirement in OSD design, modeling OSD, review model result, and Poncat demo on OSD. Introduction. We look at why urban development will cause flood. We have two snapshots here. Left-hand side is taken on year 2001. Right-hand side is taken on year 2011. Both of these snapshots I take from Google Earth. So from these two snapshots, we can conclude two things from the urban development. The previously vegetated catchment now are being covered with hard surfaces such as roads, roofs, and paving. Hard surfaces prevent stormwater from soaking into the soil. And stormwater is carried away by a series of line, straighten, pipes, and drains. So what will these two impact bring at the end? If that development is without detention facility, those two impacts will speed up the flow and increase the quantity of stormwater because the roads, paving, drains collect the water more efficiently. And the end result is cause flooding elsewhere in the catchment. Speed up the flow is because the drain is already in line. It's not like a lateral stream flow, more slower, and it increases the quantity because all the previous pervious area has been covered with hard surfaces. Like roads, housing areas, those areas are not pervious, they are impervious. So development will increase the quantity and speed up the flow. This is the reason unplanned development will always cause flood. Here are some random pictures taken from internet about the flood that happened in Malaysia. Now we look at the damages caused by the flood. This one is taken from DIG Malaysia and Malaysia National Security Council. From this brief report, we can see that even at the previous years, 1967, not even very developed at that time, but there are some states prone to flooding like Kelantan, Terengganu, and Pahang. Even at the old times when these places are not yet very developed. So why these places, these states are prone to flooding? There's a reason for it. We look at the location of these states, Kelantan, Pahang, and Terengganu. We read the description here. The hardest hit areas are along the east coast of Peninsular Malaysia in the states of Kelantan, Terengganu, and Pahang. The city of Kota Baru was particularly hard hit. For Malaysia, December is a part of northeast monsoon. So this pointed to the north. Northeast is this direction, slanting area, this slant area. This is the northeast direction. At the end of year, around December or January, is northeast monsoon. The monsoon rain can be very, very heavy. We look at how heavy it is. We look at this scale. The rainfall depth is about reaching 1000 mm within 1 week. Normally this amount of water is, for a normal rain, it takes 1 year to reach 1000 mm, the rainfall depth. But for this monsoon rain, it can reach until to 1000 mm just in 1 week. So we imagine the amount of water being poured onto these states. So this is a reason why at the end of year, we can see a lot of flooding happen to these states at the old times and even now. It's because their location and the northeast monsoon. This one is another 3D image. Both are same images. This one is in 3D. Introduction, what is OSD? I'm sure you have already know and familiar what OSD is. I just go through roughly. OSD is on-site storm detention, and it is a quantity control facility. It controls the volume of runoff. The functional principle for OSD is it collects the storm water that falls on a catchment, storing it temporarily, and then releasing it slowly at a controlled rate so that it doesn't worsen the downstream flooding. It will not solve the existing flooding problem, but the intention of OSD is to give zero impact on new development. The OSD types, there are 3 types of OSD. We look at this one, a typical underground OSD. These are the inlet pipe. It can be 1 or 2 or 3. These are the inlet pipes. The water will flow through the inlet pipes and then fill up the storage tank. If the water overflow, it will flow out from this overflow rate. And this is an outlet pipe, and there's a trash screen to screen out the trash so that the trash will not block the outlet here. So this is a service ladder. This one is a typical below ground OSD. We look at another type, above ground OSD. From just one look at it, for normal people, they cannot identify this is a above ground OSD. But for those who have already designed a above ground OSD before, they see this is a BCP here, and there's a wall surrounding this landscape area. Most definitely, this one is a above ground OSD. So how does this whole thing work is, the surrounding wall here has made this landscape a storage area, and the storm water will go inside this DCP, discharge control pit, and this discharge control pit is actually a square or rectangular chamber, and there's a small orifice connected to this DCP to the roadside drain, and water will flow out from this small orifice to the roadside drain. The water will flow from the higher area to lower area, and then into this DCP, discharge control pit, through this orifice, and at the end to the roadside drain. This one, a little drop here. This one is a secondary outlet. If this above ground OSD overflow, water will overflow from here and then flow down to the roadside drain. This is a above ground OSD. This one is a composite storage OSD, above ground and below ground. Very simple. The water flow from the higher land area and then fill up the underground OSD. If there's a lot of water, the underground OSD will be full, and then the water will be stored above ground. We look at why we choose OSD. OSD is a practical alternative when the land is not available for community-based detention basin, or the development is very small. It's only 0.1 hectare. In the submission list, it's written there, if the development is equal or less than 0.1, we can use OSD. If larger than 0.1 hectare, we need to use detention pond. But case by case, this is the general rules are written in the submission list. We look at the main advantages of OSD. OSD can prevent occurrence of frequent flooding as a result of new development. The frequent flooding here refer to small rainfall, like 2 years of ARI, 5 years, and 10 years. This small rainstorm is referred as frequent flooding. And another advantage is flooding problems are not transferred to some point in the downstream catchment. The intention of the OSD is to give zero impact on new development, not to solve existing flooding problem. The OSD main disadvantage is lack of owner awareness or willingness to undertake maintenance of the OSD. No matter underground or above ground OSD, it has a discharge control pit and it has an outlet. That discharge control pit needs maintenance. Look at maximum requirement on OSD design. Since OSD is for small development, so the maximum recommend to use rational methods to estimate the peak flow, the Q. This formula is only valid if the catchment is less or equal to 80 hectares. This formula is used to calculate the Q of pre-development and post-development. This formula is very simple to use. So maximum recommended, the first method is rational method. Rational method is being used to calculate Q. So what about estimating the size, the volume of OSD? To do that, maximum recommend to use Swinburne method. Swinburne method is being used to estimate PSD and SSR, and then later on the PSD and SSR will be used for OSD sizing to get the storage volume of the OSD. We use the Swinburne method. Okay, we look at what is PSD. PSD is permissible site discharge. Let's say one area has been developed. What is the permissible site discharge? What is the allowable Q for that newly developed site? PSD is a Q, which is a meter cube per second. In order to calculate the Q, we need the frequency of the storm, the ARI year. To get the ARI year, so how do we know what ARI year to use? It's actually based on the receiving drain capacity. Let's say the OSD is discharged into one drain. We look into that drain is designed for how many years of ARI. This is how we determine the frequency of the rainstorm. Because to calculate Q, we need, if we refer back to the previous formula, we need CIA. The I stands for rainfall intensity. The rainfall intensity depends on frequency of the storm we choose. If we choose 2 years, 5 years, or 10 years, the higher the year of ARI, the heavier the rainstorm is. So to calculate the Q, we are using this formula. So we need I. In order to get I, we need the ARI year. So how do we know which ARI year to choose? To calculate this PSD, we need the ARI year. So we see the receiving drain capacity. The receiving drain capacity is designed to how many years of ARI.